Hello there once again. In this fourth lecture video for work and energy, I'll be discussing about another very important and fundamental uh, principle in the physical world. We call the work energy theorem. Okay, so we will derive, you will see in the final equation that this theorem you've actually encountered it already, no, when you were in your high school. So let's talk about work energy theorem. So from the title of the theorem itself, it somehow gives you an idea of the relationship between these two physical quantities, no? The relationship between work and energy. At this point in time, excuse me, we already have some uh, ideas, no, on how they relate. Number one, they both have the same units of measurement. So in international system, work and energy, they're both uh, measured in terms of joules. Diba? And then what else? Uh, Work cannot be done without energy, no? So we can also say that work in the physical sense is just energy that is being transferred from one object to the other. Kaya we also have the concepts of whether the system received the energy or work is done on it, or in the other perspective would be the system does the work, so energy is leaving it. Okay, so now let's define math, or let's determine mathematically how these two quantities relate, no? Because it's not enough to say that they have the same units, that work is actually energy in transit. It's not enough. We have to have quantities, no? Kasi in science, if something is not measurable, whether directly or indirectly, we don't bother study them at all pag hindi naman siya kayang sukatin. So we will be talking about measurements. Kaya as mentioned in the beginning of this semester, it will be a plus on your side if you somehow master the systems of measurement, how to be consistent, how to report measurements with a correct number of significant figures, etc., etc. Okay. Let's start with our friend again, si Mas M. Yeah. Oops. Itong si Mas M natin has been with us, no, since the beginning of our physics adventure this semester. So let's say we have a horizontal surface here, and then our system, itong box na ito, has a certain mass M. And then when it is at a certain point 1, so position 1 niya, ganyan, let's just say that it already has a certain velocity. So meaning to say, before siya umabot sa point 1, it's already moving. And then nag-mark na lang tayo na, okay, itong mark na ito sa floor, gagawin ko itong position 1. Kasi it's up to us naman, the experimenter, kung saan yung reference for this kinematics. Okay. So let's say at pag daan niya sa point 1 from a certain reference, let's say it already has a velocity that is to the right. Yan. So velocity vector shown by this arrow here. And then we have the symbol for velocity, Greek letter nu, or it looks like the cursive for English letter V. And then arrow symbol, and then kailan siya nangyari. So this is the velocity vector initial. Now, we want this mass M to become faster as it reaches a certain position x2. So it'd say that ang gusto natin, pagdating niya sa position 2, it will now be faster. So mag-accelerate siya, and the acceleration happens by a change in speed pero constant direction. Ayan na naman ang kinematics natin. If you recall, acceleration vector, in one perspective, it can have a parallel component, if you remember. Kaya medyo marami na tayong, broader na yung way of analyzing natin this time, class. Aside from this, sabi natin si A parallel, this can also be viewed or called as A tangential pag nag curve path na pinag-uusapan. And then, si A perpendicular, the component of A that is perpendicular to the velocity vector, we can also call this as A radial kasi it's always along the radius. Further recalling, A perpendicular, this is responsible in changing the speed. But wala siyang pakialam sa direction. Speed. And then the A perpendicular, this is responsible in changing the direction. Because a change in the velocity per time, that is physically acceleration. No? Specifically average yan. Kung liitan mo itong delta, magiging instantaneous, di ba? Pag magiging dv, and then infinitesimal time interval, and then you have your acceleration, instantaneous there. And then when we apply, so this is the kinematics that we learned earlier in the semester. And then later when we went to dynamics, we learned that the acceleration is just an effect, whether the change in speed or the change in direction, it's just an effect because the cause is what? You have a cause, and the cause is a net force that is not zero. So according to the second law, if the net force is not zero, it will cause the particle to accelerate. Diba? Greater net force, greater acceleration. Greater acceleration physically means that the change in the velocity the change in the velocity happens very quickly. Yun yung ibig sabihin ng malaking acceleration. And then you have to complete the equation, you have the constant, and that constant is our mass. Yan. So, kinematics, and then dynamics, and we apply this now as we learn more about work and energy. Yan. So, yun yung hugot natin. So, balik tayo dito. If we want this mass M to become faster, such that pag i-draw natin ngayon, is intended to be horizontal. I want the final velocity to be faster than the initial. So, mas mahabang vector na arrow, pero hindi nagbago ang direction niya. Kaya, wala tayo dito. Zero ito. So, the acceleration is always parallel component lang. Kaya, alam natin na the acceleration that is involved here is parallel to the velocity. And sabihin natin, since the change in velocity is in this direction, ito ngayon si acceleration vector. So if the acceleration is in that direction, Newton's second law is saying that whatever is the direction of A, that is of course the direction of net force. Kasi ito kasi ang mag-determine kung saan ito papunta. So if the cause is to the right, then the effect is to the right. So further deducting from this or deducing from this, we say that for this rightward acceleration to happen, then there has to be a total force also that is in the same direction here. So merong total force papunta doon. So itong total force, we can say na pwedeng merong malakas na force to the right. Let's say kung F1 yan, tinulak ko siya. Yan. Tapos kung meron palang maliit na friction sa ilalim, so may kinetic friction, ayan, may maliit na kinetic friction pag i-head to tail mo siya. So, ang net force natin ngayon, initial to final, this is now the total force along the x. Ito siya. Yan. Okay? Pag i-head to tail vector mo. So, we will not focus on the individual forces here, but we'll focus on the total force. Ito lang siya. So, to start with our derivation, since this is obviously an application of Newton's second law, edi we start with that. So we say that the total force needed along the x-axis is equivalent to the product of the mass of this object and the acceleration along the x. Now, bring your mask. Next, what else? I'm sorry, I got distracted by my son. So, in this case, we know very well that the acceleration that we're talking about here is constant. Meaning, it's not position dependent. So, kahit sa ang position ng object dito, ang acceleration niya is constant. So, kung constant ang effect, constant din yung cause, yung net force natin, constant din. So, in In that case, if we want to have an equivalent expression for A, then punta tayo sa toolbox natin under constant acceleration equations. So, constant acceleration equations. Meron tayong 4. Pero, if you look at the given, wala tayong time. There are no time elements here. So, we analyze this without time element. So, hanap tayo sa equation natin for constant A, yung walang time involved is this one. We know the initial position, we know the final position, we have, what else? We don't know time, and we have V1 and V2. So, we use this equation. Final speed squared equals initial speed squared plus 2 times acceleration in the x times the displacement. Final position minus initial position. So, we want an equation for A para pang substitute natin. Bakit? Kasi gusto nating i-relate si work, si speed, at saka, yan silang dalawa. Ano ba ang relasyon ni work at saka ni speed? Yan. So, further simplifying this, we have V2 squared minus V1. Then, magkakaroon ka na lang ng 2ax, x2 minus x1. So that when we transpose 2 and the displacement, this becomes 1/2. Tapos, V2 squared minus V1 squared. And the displacement, x sub 2 minus x sub 1. So this is now our equation for AX. Ito na expression. So we substitute this there para mawala si A. So this becomes M. Meron kang M dyan. And then yung A natin na V2 squared minus V1 squared over 2 x sub 2 x sub 1. Yan. And then we still have your delta fx here. Further simplifying, we para lumabas si work, kailangan ng force times displacement, di ba? So this expression, ilipat natin sa other side of the equation. So that you have the total force times x sub 2 minus x sub 1. And then further rewriting what is left here, you have 1/2 times m V2 squared minus V1 squared. Yan. Let's bring this up somewhere there. Okay. So, displacement. Position in final minus position initial. We can substitute this with displacement vector S. And then we distribute 1/2 m. It becomes 1/2 m. Square of the final speed minus 1/2 m square of the initial speed. Total force times displacement. This is now specifically total work. Kasi total force man. Diba? Dili man tong individual. And then, do you notice any familiar expression? Yan. 1/2 m v squared. What is that? Very good. So the product of 1/2 times the mass of the particle in kilograms times the square of its speed, this is of course kinetic energy. Ta-da! Energy that is responsible in making a particle move. So any particle that has speed, you know that it's able to have that certain motion, to have that speed, simply because it has a source or a supply of kinetic energy. Kaya we also call kinetic energy as parang energy in motion. Pero if you look closely, it's just the energy that we spend so that we're able to move. No, it's still in joules, of course. So if this is final speed, then this is just final kinetic energy minus initial kinetic energy. This is now what we call the work energy theorem. So, amazingly, even if we derive this using constant force, constant acceleration, but if we widen our coverage, we can actually see, no, that if you read further, that the work energy theorem is a very fundamental physical theorem. So you can always use this for variable and constant forces, and even if the path is straight or a curve. No? So, ganyan siya ka-fundamental. So, let's look more closely here. What do we mean? What does this tell us? So, this tells us that whatever total work that is done on a system, it is needed if you want to change the kinetic energy of a system. So we can actually rewrite this also in another form, that the total work done on a system is equivalent to the change in its kinetic energy, the delta K. Walang negative dyan ha, it's just delta K. Anong ibig sabihin nito? Simple lang. If you want to bring a change in the kinetic energy of a system, then there has to be a work that needs to be done on it. Hindi pwedeng magbabago ang kinetic energy ng isang system na wala ka namang ginawang work. Okay? So parang life lang. If you want something to be done, if you want something to change, you have to work. Okay? O, pamuraging ana lang siya. So what does this further tell us? Ano bang change in kinetic energy, and what's the physical meaning when we say there's a change in kinetic energy? Then you go back to the factors that affect kinetic energy. 1/2 mass, 1/2 constant man na. Ang mass, we say, dili siya natuusabon. No? So it's actually the change in the speed. In other words, to change the kinetic energy of a system or on an object, you have to change its speed. So if the particle speeds up, where initial speed is less than final speed, so nag-speed up siya, it means that its kinetic energy initial is less than kinetic energy final. So in other words, kinetic energy has increased. Every time, mas mabilis ang particle. And then the other way around if nag-slow down siya, di ba? So if you want to make a system slow down, okay, if you want delta K to be negative, then there has to be a negative also, a negative total work also that will be done on the system. An example, say you have an object here, baliktarin natin, very fast siya sa point 1. So malaki ang speed 1 niya. Sorry, speed 1. Yan, velocity. And then after a certain distance, andito siya ngayon, you want it to be slower. V2 siya. Mas slow siya. So, for this kinetic energy to drop, then there has to be a total force in the opposite direction. Ito dapat ang total force. Total force is to the right. Displacement vector is F total is left. Displacement is to the right. So that the angle between F and S is 180. And then the work done, total work done there will be negative. Since negative ang work na ginawa mo, mag-expect ka ng kinetic energy bababa. Okay? Parang ganyan lang. So that's how related work and energy is in the context of total work and kinetic energy. We can always use, so very helpful itong si kinetic energy, work energy theorem. Ay, sorry. Bakit tumiit? Ayan. So the work energy theorem, we can also write it, of course, as the total work done by a system. We have 1/2 mass square of the final speed. Speed na ito ha, kasi kahit na papuntang left, kung merong negative velocity ang particle, pag i-square mo yan, magiging positive pa rin siya. Kaya speed yan siya. Minus 1/2 m speed squared. So the work energy theorem is very helpful in analyzing systems, even systems na nasolve na natin using kinematics and Newton's laws. Pwede nating magamit to kung number one, hindi natin alam yung elapsed time. No? Yung pag walang time element na binigay sa problem, tapos meron ng involvement ng how fast is it after some time or after moving at a certain distance or how fast should it be initially para makatravel siya ganyan-ganyan, tapos walang time involved, okay? Then that is a hint na, okay, I can use work energy theorem here. Yan. So this work energy theorem, we can, this is actually another perspective of one of the most fundamental conservation laws in the universe, and that is the law of conservation of what? Mechanical energy. Law of conservation of mechanical energy. Ayan. So makikita natin, I'll try making another video focusing on this law. Tapos makita natin, okay, yung work energy theorem pala is another way of looking lang at the conservation of energy law. Ayan. So again, regardless of the kind of engineering program that you are into, understanding the law or this law is very very important in your field later. Ayan. Okay, so I think I have to stop here and then you read more about these things. I will try again creating another video for the law of conservation of energy. Ayan. Okay, so that would be for now. Stop sharing. Bye-bye.